Today, I just try to introduce our light source, which is located at the Hefei. We call this is the Hefei Light Source. And let me get the point. Yes. So basically, today I try to introduce the soft X-ray endstation at the Hefei Light Source, and with some applications of XAS, which my group did. So I come from NSL and University of Science and Technology of China, and today the topic will be three parts. So in first part, I will be mainly overview the Hefei light source and the endstation, and then I will give the examples about XAS for identify carbon-based electrocatalysts. And then the third part will be the XAS for probing dynamic electrochemical reaction. So this is the main content of my talk. So first of all, I would like to introduce the NSIL for all of you, and basically this is the NSIL. So NSIL is the first national laboratory in China, which is set up in 1984. So which is located at the Hefei, so very small city, which is about 2-hour train to Shanghai and 4-hour train to Beijing. So with the fast train is not too far. And this is the Hefei light source. So this is basically this is the first dedicated synchrotron radiation facility in China, and at this moment it runs as one of the China's national government funded large research in infrastructures. So why mention this? Because most of our fundings come from the China government. So at this moment, HLS can provide high brightness synchrotron radiation and spanning the electromagnetic spectrum from infrared through soft X-ray, especially very strong in the VUV and the soft X-ray. So this is really different between Hefei light source and Shanghai light source. So as you know, we have the third generation light source in Shanghai, and this is basically the second generation synchrotron light source. So the characteristic wavelength from bending magnet is about 0.4 nanometer. So, and this is the history of the construction in HLS. And the first one is since 1984 to 1991. So this is the first one construction, and totally funding is about 64 million. So the main components is the 800 MeV electron storage ring and 200 MeV electron linear and transfer line. So at that time, the first four they have we had 5 beamline and endstations. So then we go to the phase 2 constructions. So we got the total around the funding is about 118 millions. So in that phase 2, we try to improving the reliability and optical stabilities. And at that time, we reached about 16 endstations and with a new ondulator. So, and after that, we got, another upgrade program. This program total funding is about 100 million. So this main arms is to reducing emittance. And with this funding, we had improvement on the more ondulator and the more beamlines and endstations. So after this construction and this upgrade program, at this moment, HLS own a fully upgraded soft X-ray synchrotron radiation with a lower beam emittance. So as you can see, this is a parameter for the storage ring in HLS, so which I already mentioned. So the beam energy is about 800 MeV, the injecting energy is about 800 MeV, and beam emittance is about the 38 nanometer rack. And the beam intensity is about 300 milliamp, and the beam lifetime is about 6 hours. So the orbital shift is about 4 microns. So this is our storage ring parameter. And with this storage ring, we have the beamline and experimental station. At this moment, we run 10. So as you can see, the red color is from the undulator and wiggler. So the blue color is from the band magnet. So basically, we have 5 undulator station and 5 band magnet and station. So as you can see, so today, since I basically not running any station, I just use. So that means I'm in-house scientist, which I use mainly the stations. So this four is what I use, very often use. The first one is the photoemission spectroscopy and station, and I also use a catalysis and surface science and station. So this is the mainly I did the soft X-ray absorption in XMCD. So and I also did some APAS angle resolved photoemission spectroscopy on my single crystal and samples. So this is what I mainly used, the annotation. And basically this is I just try to give some key parameter for this annotation in Hefei Light Source. So this is the beamline 10B. We call this photoemission annotation. So the photon source is a bending magnet. So the energy range is about 100 to 1000 eV, and the energy reserving power is about 1000 at 244 eV. So this flux is about 10 to 10 photons per second, and the beam size is pretty large. It's about 1 times 0.8 millimeter square. So the spectrometer resolution is about 50 MeV, which is they have the analysis chamber by the R3000 electron analyzer. So basically, this photoemission annotation is running by Professor Peng and also Professor Junfa Zhu. So I think he's a very good friend with also Jerry. So and so this annotation basically is mainly working on the synchrotron radiation photoemission spectroscopy and with the X-ray XPS. So they also can do the resonant photoemission spectroscopy. So they have a reactor with the condition, the sample temperature range from 100 to 950 Kelvin, and pressure is can reach about 20 MPa. So they have the 2 gas controller. So this mainly this chamber or this station at this moment is mainly work for the heterogeneous catalysis. So especially the surface structure and reaction mechanism, because they also can study the surface composition and electron structure of the metal and oxide and polymer film. So especially strong at the surface and interface analysis of the solid state function materials. So this is the synchrotron radiation PS, which they do. And the second annotation which I used is the catalysis and surface science. I think maybe now you also know this from Professor Junfa Zhu. And this is a photon source is the undulator. So this is in the first 2 construction. They put the undulator in this beamline, and the energy range is about 20 to 600 eV, and the energy resolution resolving power is pretty okay. It's about 10,000 at 29 eV. So the flux is can reach about 5 times 10 to 10 photosecond per second, and the beam size is pretty smaller compared to the bending magnet. So this beam size is about 0.2 times 0.1 millimeter square, and it can optimize further. So the spectrometer resolution is about 5 milli-EV at 20 EV. So this is the beam line, which is a schematic image. And so basically this is a undulator endostation, which is designed for this high resolution section radiation photoemission spectrum, and also can do the high resolution XPS at the high pressure. So they really have the combine some very advanced facility to this analyze, and they can introduce some gas or some other conditions. So of course, this also can do some near edge X-ray absorption fine structure, and with the low energy electron diffraction. So this endostation is pretty good, which can give the element composition, chemical state, and depth information, orientation of the molecular and electron structure. They mainly focus on the material science and the surface and interface analysis. So if you're interested, you can directly contact Professor Junfa Zhu. He is a very senior beamline scientist in Hefei Light Source. So I'm the in-house user in this endostation. So this is soft X-ray magnetic circular dichroism endostation, which we call XMCD or SXMCD. So basically, this photon source is a bending magnet. So the energy is about 100 to 1,000 eV, and the energy resolution is about 1,000 at 1,000 eV, and the flux is not so high, and it optimized can 5 times 10 to 9 photon per second. So the spot size is also a little bit larger. So it's about 3 times 1 millimeter square. So this is the real picture of this endostation, as you can see. So this is what I very often did. The soft X-ray absorption near edge structure, and in this endostation. So at this moment, as I mentioned, this energy can from 100 to 1,000. So which is really very sensitive to the light element and the K-edge of the light element, and also the L-edge of the transition metal element. So this is what I very often use, and but you may confuse why they call this name, because the endostation also mainly work on this XMCD. So they try to study the magnetic materials about for the physics and for the electron spin, and for this kind of study. So, and that is why they're basically at this moment they try to upgrading with the magnet field. So they are still under construction. So it's since the end of the last year. So the final endostation which I want to show is the angle resolved photoemission spectrum, the APAS. So this is also the undulator endostation, which with the energy range is about 5 to 65 eV, and the energy resolution is can reach about 1 milli-EV at 10 eV. So the photon flux is pretty okay. It's about 10 to 11. And the support size can optimize to 0.4 times 0.2 millimeter square. And the vacuum can go to the 7 times 10 to minus 11 too. So this is the annotation of which the upparts. So the mainly focus on the experimental technique is the upparts, and meanwhile they also combine with the molecular beam epoxy and also low energy electron diffraction. So that means they can in situ grow some materials and also treat materials, do some treatment on the materials and study the upparts. So they try to tell you the band structure and electron structure in these materials. This is also I did some 2D materials and also some topologic insulator in this annotation. So then this is the first part which I try to tell. This is the overview for the Hefei light source and annotation. So I would like to answer any question for the first part.
Thank you. My first question is, what are the long-term plans for the Hefei light source? Is there any plan to do further upgrade or build a new ring, or what's next? There's been this wonderful progress, but what's the next step?
Thank you very much. This is what we are, our leader and our whole the laboratory think about. So actually since 3 years ago, so we got the funding for start the plan to pre-study the new light source, because it's fourth generation light source. This is I will show the last in my last slide. I will show the picture. So basically, and another news is we already after 3 years pre-study, and this year and just last month we submit our proposal to the government, and this next month will be the decision. So and this one will be about 3 billion funding to set the new first generation X-ray ring.
Very nice. It would be. I remember I visited. It would have to be outside the city.
Yeah, exactly.
Okay.
It's not too far. It's not too far. By the car, it's about maybe 40 minutes.
Okay.
It's not too far, so it's still okay. And because we already sent this proposal, and we already got the plans, and the plans already be passed. I mean, be fixed by the local government.
Good. That's very exciting. Matthew Marcus, you have a question?
Yeah, I was wondering if infrared is in your portfolio or planned to be.
Yeah, I think this is a very good question. So in the old light source, we call the Hefei light source, we do have the infrared spectrum and microscopy, and we try to study some high key materials. And in the new light source, yes, we do have, but not at the Foster construction. We already put in this second construction. That means the Foster, we will set up, we plan 9 beamline and endstations, and then in the second phase, we will put another maybe around 10 endstations. The totally endstations of beamline in this new light source will be 34 around. And
some of them will be infrared.
Yeah.
Good.
So, and for the infrared, we also have the free electrons at this moment. It's just be constructed. So I hope it may can provide the using for the user maybe at the end of this year, because it's still under construction, is almost finished.
Yeah, at ALS we have FTIR microscopy, and you can't do that at a free electron laser because you need polychromatic beam.
Yeah.
Okay. All right. Thank you, Lee. You should continue.
Okay. Thank you. Thank you very much. So I will, in the following, I will just show some examples which mainly come from my group. And as I mentioned, we are the in-house scientists. So we try to use the light source. So this time I just show some examples. So as I mentioned, and why when Matthew says this is a carbon nanotube, I'm very interesting because for my PhD study and for my postdoctor, I did a lot of work on the carbon nanotube. And this is a carbon nanotube which I did. And in around 10 years ago, we tried to build some new carbon materials. So this is mainly made by carbon with boron and nitrogen. And we try to build the this is a triangle system, because as you can see, they have many materials not be realized until now. So we're very interested in that. That is why in 2012 I joined the National Synchrotron Radiation Lab, because I know here they have the software X-ray, so which I already show, and I want to use this software X-ray to study the light element like the boron, carbon, and nitrogen. Of course, with the oxygen and phosphorus, this is also very interesting for the carbon. So with after I joined, I found yes, this is not so high resolution because this is a second generation light source. And then I try to put some metal and combine the metal with this carbon. So we think maybe if we cannot get the new nanostructure, we can study some new energy materials with some combine a different kind of element. So that means we can do some atomic engineering for these carbon materials to get some to tune this atomic structure in the nanocarbons. Then the motivation is to realize some electronic structure regulation and also change the physical and chemical properties for these carbon materials. So then, and this is the first examples. So we try to build some carbon with some transition metal. This is we selected nickel. So we found we developed one process to make some very unique structure. So in this unique structure, you can see we tried to use the carbon as shell, which is a cover the nickel particle. But between the nickel particle, then we will have the nickel oxide, but not too much. So by the normal tool, you cannot really identify this structure. So in that case, we select the synchrotron radiation technique. So here, as you can see, by the TEM and XRD, you will see this material is very unique, very tiny particle, and with the metal inside and with the carbon outside. So in here, you want to know how the carbon shell interface with the metal. So does there any chemical bonding, or how this chemical bonding contribute to the properties? So this is we combine XPS with XAS, so to identify the interface and the superstructure. So here, as you can see, the nickel XPS of this hybrid system, you can see this do have the crystalline peak in here, and you can identify. And you also can see the red color. The red color is, you can clearly see the high energy side of the nickel L3 edge. So this is the nickel LH, the spectrum, and you can see combine this is the nickel foil and the different kind of oxide the sample. You will see that some clear peak appear. So by this. And we can see, so compared to the nickel foil and the shorter peak A, you can see here, and at the high energy site, and also this is the splitting of the L2, we mark here as the B and C. You can see by this we can say this interface structure really work and really have some chemical structure between the nickel and nickel oxide and the carbon. So this is also carbon KH spectrum. You will see they have clearly show after the acid treatment that clearly show the peak here. So this is the additional peak, and by this spectrum we further study the XAS and also XAS on this is the heavy metal. So as you can see by the normalized nickel KH XAS spectrum, you will see that if you compare to the pre-edge, they do show some shifting, but compared to the nickel foil and nickel oxygen foil, oxide foil, you will see the valence state is not, it's very close to the nickel foil, it's not too far, and that means this is just slight oxidized. So, and by the XAS analysis of this, by the R region, you will see clearly by the fitting, you will see this is really can confirm this formation of the ternary interfacial structure. That means how say this ternary? Because that means carbon with the nickel oxides, they have the interface, and the nickel oxide with the nickel, they have the interface. And meanwhile, the carbon also with the nickel metal have the interface. So how this interface work? So we do the simulation, and we can see clearly the nickel-nickel oxygen interface can really decrease the energy barrier of the formation, which is a really, for example here, so which is a really a more favorable for the transition state, and the facilitate the formation of the absorption hydrogen. That means you can use these materials as a catalyst for the electrocatalytic water splitting. So that means this is what we understand, how to identify the ternary interface and to understand how this work for hydrogen evaluation reaction. So this is the performance. Since this is the XAS club, I do not want to show too much about the results. Just want to show, okay, by the XAS, we can identify the interface between the metal oxide and the carbon. So then we go to the second examples for the carbon. So since we have some metal particle, if you decrease the metal particle to the molecule, to the atom, even to the cluster, you will see you really decrease the size. So here we want to decrease the dimension of the materials to the two-dimensional and to one-dimensional. So we want the high interaction or high accessible space for the catalyst. So here we selected the carbon anion as a spot, and then we use the ELD to deposit some particle or some not only particle, and we try to decrease the particle into the atom. So this is almost a single atom in here. You can see which is located, which is supported by the carbon anion. So and this is too tiny. So we need the technique to identify the structure. So here, as you can see, we try to use the XPS first to understand how the atom combine or some interact with the carbon support. So here we found if you if you control the oxygen functional group in the carbon anion, you really can control the atom, the platinum atom content, which is mounted on the carbon anion. So that means this oxygen group is really key parameter for this kind of mounting. So then we also use the XAS to study the structure, because this is so tiny atom. So we study the PT XAS, and as you can see, this is the R region and this is XAS. You see clearly, if you see this, we can clearly say, okay, this PT in there is a single atom. They do not have the PT bond in there. the most case, they bonding with the oxygen. So by this characteristic and by this characterization, we really can give the atomic model. So we set the atomic like this. So in here, we put the PT combined with the oxygen group in the carbon anion. And we really simulate the thermal stability. We found if you directly put the PT on the carbon anion, it's not thermal stable. If you put some two oxygen as the arm to catch up this PT, they're really stable. So, and meanwhile, we do this very important simulation. We found if you put the PT, if you simulate the carbon anion, if they do not have any PT on the surface, if you apply the potential, electric potential, you do not see any local field. But interestingly, if you put the PT on the top and on the surface, you will see when you apply the potential or you apply the electric field, you will see some local electric field. So this is really called the tip enhanced local field. So how this works? So we calculate the free energy diagram. We found if you have this kind of things, if you try to put the proton in here, since this is a local field, and they really can, if you put 1, 2, and 3 proton in there, you will electron in there, you really see the two proton can combine together to form the hydrogen atom. So that means this local structure really works, really contributes to the hydrogen evaluation. So this is the experimental results. As you can see, this is the first. This is a single atom really stable. So that means, as you can see, this is a by 100 hours stabilized test. You will see, because if you do not have any chemical bonding on here, if you do not understand this chemical bonding can control this single particle, is a single atom, and they will be lost during the reaction. But by this, the second very important thing is we found by the optimized electrocatalyst of this materials, you only use about 0.27 watt% PT combined with the carbon anion. You can reach very comparable HER rate, which is really similar to the 20% PT loading. So that means, as you can see, you really decrease the normal metal about 100 times. So this is a really economic way and with a high rate. So that means we give the story like you have either electrochemical and the electrocatalyst. You have really particle which you use for the electrical chemical reaction, but inside that do not work. For example, you hide many atom inside. Only the surface atom which is contribute to the reaction. So this is the you also know they have the story about the stone. So which is a very famous story. So basically in this family, there are many people in this family, many members in this family, but only very few people contribute to the economic value of this family. That means many other people want to contribute, but they do not have the chance. So if you put them all out, they can contribute. So in this case, we make some cartoon. Means here, as you can see, if you apply electric field, the first they will form some local field, which is they can absorb the proton here, and the proton will be combined together to form the hydrogen. But meanwhile, as you can see, this is a carbon anion. So carbon anion is a shell, layer by layer. So this is when you apply the voltage, this shell, between two shells, they really can work as a capacitor. So in this capacitor, they can collect the electrons. The electrons always is like electron source. they always can provide rich electrons to this tip. So that means by this tip, by this single atom, you really can enhance the electrocatalytic efficiency. So this is the first story I would like to tell. So about the carbon-based electrocatalyst. Yeah, I would like to answer any question for this part.
It's very interesting.
Yes, thank you.
What's I'm not sure how to ask the right question. Is there a way to get away from platinum? Of course, there's a large trend in catalysis research to try to use less precious metals. Do you get some special idea about how to make the catalysis effective that you can transfer to not using platinum?
Yeah, this is a very, very good question, and we are working on this. We recently published some paper in agronomy and also advanced materials. So we try to use a transition metal to replace the platinum. So as you can see, in the catalytic activity, so the platinum and for example, platinum, the palladium, and also the other noble metal is really, they have the highest activity, but they do very expensive, right? So in here, we try to we try to use a transition metal to replace the platinum. Yes, we do works. So we use a cobalt and we use the iron. Yeah, it works. Yes, compared to the platinum, you can see the efficiency a little bit decreased, but it can be acceptable. So this is the first try. We try to replace the platinum from the single atomic catalyst. The second step we try to replace. Meanwhile, we also replace the carbon support. Since we want to extend the field, we try to use the transition metal, and which can be supported by the, for example, phosphide, oxide, and some LDH. So this is really works, but it's a little bit difficult because you need make some vacancy, you need to make some defect on this support. You want to use this as a trap to catch the single atom, because in the single atom catalytic, the main challenge is the stability. If you do not have the very strong chemical bonding and you do not have the very strong interface during reaction, the single atom will be lost.
Yes.
So in this case, your performance will be decrease very faster. So this is why we are doing it.
Good. Okay. Excellent. Thank you. You should continue.
Okay. Thank you very much. So in the following 50 minutes, I will try to tell some story about the user XAS, try to probing the dynamic electrochemical reaction. So as you know, in many chemical reactions, for example, hydrogen evaluation reaction, oxygen reduction reaction, OER and CORR. So this is during this reaction, because you will reach electrolyte, right? You will put it into the solution, and you also have the applied field. So in this case, you will always see very often the materials, the catalyst which you put is changed. So especially this changing will be mainly dependent on the applied voltage and pH value and electrolyte. So how to understand this? So this is what we are thinking about. So that means you put the electrolyte, and we call at this moment we call the pre-catalyst. You study the performance and you found, okay, this performance looks very good. But meanwhile, the other group say, okay, this performance is not good because the synthesized way may be different, right? So what's the reason? So because the reason is like you try to make the relationship between the pre-catalyst with the performance. But if you really look into the structure, look into the reaction, you will see in many cases, the catalyst, the pre-catalyst will be self-reconstruction during the electrocatalysis. So that's why you need the operando or in situ analyze. I think in coming talk, the scientists from the pseudo university were talking about operando study. So you need some operando or in situ analyze on this pre-catalyst to understand if this change. So if they change to the true catalyst, then you understand the real structure of the true catalyst, and you build up the relationship between the true catalyst with the performance. This is the right way. So that's why the most important things you need to build, you need the bridge. The bridge we understand is the operando or in situ analyze. So that is why you need to design the very suitable in situ cell, and you need to develop operando XAS, especially the hardware XAS, to analyze technique and to probe the dynamic structure. So, and then you can build this performance. So this is just some picture which we used for the XAS test. And this is examples. So first, so for some structures, as you can see, they not totally reconstruction. So there's not totally change the phase. Most of the cases they just change the surface. As you can see, we make some sample, the model catalyst. We put some iridium incorporated with the cobalt hydroxide. So here, as you can see, before the reaction, you will see some. Of course, they do have the very tiny atom here, but most of the cases they have some cluster. So we call this a nano cluster. So in here, before the reaction, you will see by the XPS and also by XAS, you will see they do show very clear iridium nanocluster with cobalt hydroxide. So that means you will see very clearly they do have a very tiny iridium cobalt bonding in there, which is come from the supporting and interface. But interesting things like if you put into the reaction, and if you check during the reaction, if you check this is the reference sample, this is radium oxide, and this is our initial sample. This is after actually OER samples. You will see compared to you selected the reference sample, you will see clearly after reaction this sample change. So that means before you do the reaction, this is the pre-catalyst. But after reaction, they change from the cobalt oxide iridium nanocluster, change it to some transformation to the alpha cobalt hydroxide, and also bed phase to the bed phase cobalt oxide oxygen. So this is means they change the phase. But meanwhile, the iridium nanoparticle also change to the iridium oxide. So that means during the reaction, this active site, not the initial materials, it's changed to the iridium oxide and cobalt oxide hydroxide. So that means these two guys is the real active site. So this is what we found by the XAS. So then this is just changing in the surface because this is layer materials that the electrolyte it's very hard to reach the inside. So in that case, we synthesized another model catalyst. We call this either cobalt chloride. So this means before the reaction, you will see clearly the atomic structure. This cobalt bonding with 4 oxygen and with 2 chloride bonding. So that means they have the 6 coordination number. And meanwhile, in this material, they only have the 2 oxygen be replaced by the chloride, right? So if you see, they do have the 6 coordination oxygen here with the 6 oxygen. So this is a high TM to confirm this structure. That means, and this is XPS, which is show the valence state of this cobalt and chloride. So here, this is clearly show the materials. And interestingly, during the OER behavior, we found very interesting, during CV scanning, the active surface area continuously increased. if you see from the first cycle to the 100th cycle, so the solution change, the solution color even change, right? As you can see, the catalytic active continuously become better and better. So if we understand, and by the control sample, we can see during reaction, the lattice chloride will be etched away because by the reaction. So the breakdown the cobalt chloride bonding will be never reversed because the chemical reaction forbidden, right? So in this case, the OER performance continuously increase with the CV activating process. So here we try to understand what happened. So here, this is the after reaction. We study the materials. We found the materials really change, totally change. So as I mentioned before, in the iridium chloride, the cobalt hydroxide is just a change on the surface, but this guy is a change totally. So as you can see, they have many structure defects. And in this structure, you can clearly identify the structure by the electron microscope. By this, you can see this is not cobalt oxychloride. It's changed. It changed. This is a really reconstruction to the bed phase cobalt oxide hydroxide. So that means this material is totally changed during the chloride being etched out, right? So by the XAS, this is a really fine analyze. You will see clearly, and by this, of course, this is not directly evidence. The evidence is like, so you can see the materials. We also synthesize the cobalt oxide hydroxide bulk materials as a reference. We found this structure really very close to this one. We also use the reference sample for the OER reaction. We found the materials of we directly synthesize these materials is no anion active. So that means the active sites not come from the cobalt oxide hydroxide, but after your reaction, you really found the material change to this guy. So what's the reason? So if you combine the XAS analyze about especially about the extended range here and combine to the simulation, you will see. So during your reaction, you found the chloride etch out that cannot be back. So in this case, you will have the cobalt have only 4 oxygen bonding. So this 4 oxygen bonding the cobalt here. This is the blue color, light blue color here. They only have the 4 oxygen bonding. So they have the unsaturated bonding here. So that means compared to this bed phase, this active bed phase cobalt oxide hydroxide to the reference sample, you will see the difference between these two samples is this guy. So by the simulation of the gypsum-free imager for the OER, you really found the real active side is this, not the cobalt with the 6 oxygen, but cobalt with 4 oxygen. So by this, we can clearly understand the suggest the coordinatively unsaturated cobalt 4 oxygen site served as a real active site for the OER. So this is what we understand by XAS combined with the simulation. So the last example is this. We understand you have the layer materials, you have the real large space in the interface, right? You can put some agent atom inside the channel, and you can use this functional group and to bonding with the agent atom. So here we try to put the metal atom inside the channel, and we try to understand, because for this kind of mixing, when they use for the electrodes, the structure is very easy to break it, very easy to destroy during the reaction. So if you put atom here, you want to have some chemical bonding here. So how to identify? So then we use the XAS to identify the bonding. So we found when you put the ion here, you put the metal ion here, you will see the ion will bonding with the functional group. Most of the cases is bonding with the oxygen. So the atom will bonding with the oxygen, then bonding with the host materials, and they form the very stable structure. So that's why you can see by this design, you will see clearly the very excellent stability of the lithium storage for the electrode. So here, and we also want to try to understand during your reaction, during your lithium charge discharge, does this structure or does this atom contribute or does this atom change? We found during structure we use the XRD, and we found that structure really expanded and shrink. And we use the soft X-ray, oxygen KH and fluorine KH. We try to understand, does this functional group contribute to this lithium storage? We found, and during the reaction, the fluorine not change. Most of them not change the spectrum structure, but the oxygen do change. That means during the reaction, the oxygen do some positive contribution for this lithium storage, but the fluorine not contribute. So that means this also tell us if you want to increase the performance, you need to try to remove the fluorine and try to increase the oxygen group. And this is just a ex-situ study. So as like we try to use a soft X-ray to study the functional group in these materials, but we really want to understand, does this is the metal atom contribute? So that's why we also try to build the homemade in-situ battery cell for XAS test. So here we selected the tin intercalated with vanadium carbide. So we found during the charge discharge, and we do the in-situ scan, we found here, we selected the reference sample. We can calculate the valence value. And as you can see, by this, if you see the vanadium KH, you will see the valence, the average valence edge, valence can change from 2.66 to 2.75. That means during the lithium storage, the vanadium really contribute. So that means this vanadium is an intercalated atom, but they really contribute to this lithium storage. But meanwhile, if you see, sorry, this is the host material. This is the vanadium carbide. So the tin, if you see this, you will see clearly during your scanning, you will see the valence value can change from 3.385 to the 3.42. So this is the average valence. So that means you really can give the conclusion about during the charge discharge process, and in these materials and the hosting materials, the metal contribute to the lithium storage. And meanwhile, in the collected, the atom really also contribute, and also the functional group contribute to this performance. So I think this is what I try to tell you the third part. So to answer Jerry's question, this is our design for the new, the first generation. We call this is the HAF. This is Hefei Advanced Light Facility. So this means our engineering is half, our science is half. Yes, this is what I want to say.
Thank you. Very interesting examples, and it's very nice to hear the good news. Hopefully, the good news about HAF. That'd be very nice.
We really look forward to this good news.
Yes. Just a few questions on the cobalt double hydroxide, cobalt OH2, the where you had the iridium. If you go back to that slide, I was surprised at the magnitude of the structural changing. The iridium.
Iridium, right? This one?
Yeah, that slide, exactly. Figure C. You have a very, very big change in the cobalt zones. What is the coverage fraction of the iridium? I'm trying to understand why you have reaction to the cobalt happening away from the iridium atoms. Are they mobile, or what's happening?
Basically, as you can see, the structure is like this. So the iridium, some of the cases so this is in situ synthesis. During synthesis, we put iridium with this precursor, and during this form, the layer form, then we will have some very tiny iridium atom and also iridium cluster, which is really trapped in this lattice. Okay, and during the reaction, and most of the cases, the cobalt hydroxide will be changed to the oxide because this is the electrolyte. So the electrolyte will be changed this. That means the cobalt oxide will be oxidized. So they will change, especially they will change it on the surface. But meanwhile, because they also have the iridium which is located at the surface, as you can see here. So, and they also change by the oxidized. So that is what we understand here. And also this is the iridium here. This is the cobalt here. So as you can see, if you see the cobalt after oxidized here. So this is the after OER. You will see the sample totally change from the initially the red color go to the blue. As you can see, if you compare compares here, you will see the main peak is the cobalt, and cobalt oxide.
Okay, I think I understand. Matthew Newville, you have a question?
Yes. Hi, Lee. Thanks. That was very nice.
Thank you.
Set of work. But I was struck that you showed a lot of hard X-ray XAS on cobalt and iridium and iron and other elements. But you also mixed that with soft X-ray work. And were those at the same beam line and beam runs and on the same samples? And if they're not on the same samples at the same time, what's the sampling depth differences in those measurements?
Yeah. I think this is very good question. So since, as I mentioned, the soft X-ray, what I did is most located in the XMCD's endstation in Hefei Light Source. As I mentioned at the first slide, the Hefei is about 2-hour fast train from Hefei to Shanghai. So Shanghai, they have the third generation, the hard X-ray light source. This is the energy about 3.5. So that means the sample is the same and the reaction is the same. So we always synthesize the control sample, synthesize the typical, as a model catalyst. So we synthesize the model catalyst, which is can combine the soft X-ray with the hard X-ray. Because, for example, for most of the in-situ study, we, as you know, soft X-ray is really hard to do some in-situ study. So that's why we try to build. We really finished the construction of the new endstation, which is supported by the Suzhou University. They give the 10 millions to build up the new in-situ energy endstation in Hefei Light Source. We try to build up the in-situ soft X-ray endstation. And meanwhile, most of the cases I did, for example, I did this. Most of the cases is in Shanghai. As you can see, this one is the BL14W1, which is a Shanghai light source. So most of the cases, I use the soft X-ray to study the light element. I use a hard X-ray to study the metal. So I combine this material and combine this data because this is at the same sample. So I combine this data and I combine this simulation together to try to understand the whole story, the whole structure.
Okay, thanks.
Thank you. Thanks.
All right, last question from Yang Ha.
Hi, so in your lithium storage project,
Yes.
it looks like a lithium ion battery to me.
Yeah.
and you have a layered structure. And I was actually surprised to see that your cycle number can go to 15,000. Usually the layered compound is not stable upon lithium delization. So do you see any structure rearrangement or transition metal cation migration upon your cycling?
Yeah, this is a really, really good question. As you can see, this is also the reason why we put the metal here. So we put the metal here to stabilize the layer structure, as you can see, because they will be combined. They will form for example, in the vanadium carbide, they will form the vanadium oxiding. The oxiding group is during the use HF etching, they will be oxidized a little bit by the solution. You will have the oxiding group here. Then you put the ion in there. They will be combined. Okay. Yeah, they will form the metal oxiding and the metal, right? So this will be stabilized. You are really, really right for the lithium storage. So this is not a real lithium storage, lithium ion battery. So this is a battery combined capacitor. So that means the battery with the capacitor behavior. As you can see, they do this layer structure. That means the contribution, the stability, first is come from the stabilizer of the intercalating metal, because they formed this kind of chemical bonding. Meanwhile, by this we also understand the functional group also contribute to the lithium storage, and by this we understand the metal, not only the vanadium but also the intercalated outer metal also contributed to the lithium storage performance. So that means this is a battery combining the capacitor, and meanwhile the intercalating element really works for this stabilized. As you can see, this can really go to this very long
cycle numbers. Yes.
Yeah.
Okay, so then another question I'm having is, do you observe any transition metal migration, say, just between different layers in your experiment?
Yeah, this is a very good question, and we try to, for example, here. So during this, we try to see, we do see some, for example, intercalated the atom, the metal that do change the valence state, right? And we cannot really see if, for example, if this either really become larger, or especially by the different kind of layer. So at the same layer, they may try to aggregate together, but by the different layer, since you can see they have the interlayer here, they have the interlayer material here, so they will maybe block these two guys together. So that means in the same layer, this metal during the reaction, this metal may be a little bit aggregation, but the different layer, I think, is not so easy. This is what I suggest, but I do not have the evidence.
Okay. Thank you.